Throughout this chapter, we've talked about our single bonds and our double bonds and our triple bonds. We've really focused on the shape of the central atom. We haven't really talked a whole lot about the implications for the shape of an entire molecule. But we should do that right now. And so what we're going to find is that single bonds are going to give one sort of a behavior, while double and triple bonds are going to do something a little bit different. Now, our single bonds are going to be able to rotate like this. And so this whole section is going to be able to spin around like a pinwheel. Now, why can't it? Simply put, there's nothing stopping it from doing it. We're not changing any of the bond angles either. So we're keeping our 109 degrees between these two bonds, keeping 109 degrees between these two bonds, just picking a few at random as a quick example. And so our angles are all staying locked into just what we thought they would be. And you can see down here we're actually inflating this a little bit to look like they're orbitals. But I want to remind you that typically when we draw our orbitals, we only show 90% of the time the electron is in this range. If we wanted to show where the electron is more and more often, we'd have to actually inflate that balloon further and further out. Now I want you to visualize something, just to front load a big realization that pops in a lot for organic chemistry later on. As you inflate these further and further outward, in other words, as we consider a slight possibility that there's the electron out here, we're eventually going to get to the point where these two balloons are bumping into each other. And they're going to be pressed directly against each other as we have them drawn here. This one is going to be bumping straight into that one. This one will be bumping straight into that one. And these two down here will be bumping straight into each other too. What we would expect to happen as we kept inflating them, we'd expect this to twist a little bit to it's more like we see above, where this atom is sitting right there in the cleft between these two atoms here. So it'll be sitting right there in the notch that the two orbitals form. Now that said, you can also remember that these balloons, once we've inflated to that point, there's a very low chance that the electron's out there. So they should still be able to push past each other pretty easily. This is just going to make a slight preference, almost like a couple of little notches. Picture, with some of the knobs that you turn, like a volume knob or something. Sometimes there's like a little detente that you just feel like a very gentle click that you can just keep spinning right past whenever you want. That's what we're talking about for the spinning motion. It can spin freely, but there's going to be certain spots where maybe it just kind of clicks into place and has a tiny bit more stability. That's important when you get to organic chemistry, like I said, but it's not something we have to focus on a ton in this chapter. I just want you to have that for when you go on in other coursework, to realize one of the reasons that we can have some certain geometries we expect. But by and large, sigma bonds, our single bonds, are going to be able to spin pretty freely. And if we chain lots of these together, that means if all we have are single bonds, the whole thing can be arranged like spaghetti. So if you picture one of our linear alkanes, something like hexane, 2, 3, 4, 5, 6, remember hexane, and we have all of those hydrogens around it. I'm not going to draw them in right now. We can have this thing shaped however we want it. It can have twists, it can be shaped like a C, it can be sitting in a straight line. This is going to be really floppy, like a piece of spaghetti, because each of those little Tinker Toy pieces can keep spinning around their bonds and rearranging at will. But what if we wanted to build geometries with our Tinker Toys where we lock something into place? Well, the way that you used to do that was you'd try to use something flat, or you'd try to lock it in by having two sticks holding it still. That's what we're talking about with our double bonds and triple bonds. Because what's going to happen is that pi bond that we form around the sigma bond is going to lock the shape. And so you won't be able to rotate it anymore. It's going to stay very planar. So here you can see that we're going to have a double bond between these two carbons. Our sigma bond, I'll just specify it's the bottom one. I'm making that up completely. One of these bonds is going to be sigma. The other is going to be pi. This is going to be our sigma bond right here. And on the top we're going to have our pi bond. And the bottom is still going to be the other half of the same pi bond. Remember, ice cream sandwich or hot dog bun, whichever way you'd like to think of it. This sandwich, the bread on the outside, is the same piece of bread, just cut in half. Now if we look at each of those two individually, from the top view you can see really easily our sp2 hybrid orbitals that start out making the sigma bond to start with. But they overlap for that unshared set of electrons originally, the pi orbital that was sticking up and down, so we're looking straight up and down at right there. That one bleeds further and further to the side and ends up merging together to make these pi orbitals. And that's the one that looks like a hot dog bun or an ice cream sandwich. Above and below the rest of the molecule. Now the thing is, if you tried to spin this like a pinwheel, you could, but in the process, you're going to pull these to the point where they can't be sharing anymore. In other words, if you've stopped these two orbitals from sharing, you've broken the second bond. So you can twist it until this actually does break, but you have to put in an entire bond's worth of energy to break that bond. So it's going to cost you a lot of energy. Over here, it costs you almost nothing to spin them. Over here, it costs quite a bit. And so if you have a biological molecule that needs to have a very specific structure that's strong, any spot that needs to be strong, you're going to find double and triple bonds there. Any place where you need to be able to have motion, where you need to have something that can act like a hinge or that can rotate and snap into place, you're going to have single bonds, sigma bonds, in that range. And so we can see that we're starting to get a whole toolkit of properties based on these low-level properties. And these small-level properties are giving big-level properties that will give all kinds of function at an even higher level. That's why I really say the small parts of a system are giving us the properties of the whole.